enjoy as well. So just real quickly, I'm Kim Wilkins. I am an EDD student at UVA and the founder of Tech Girls and one of the facilitators for this workshop. And this workshop is partly CS Institute, which is a program that's been running for years now and is available to anybody, and then partly a customized version of the workshop for some Charlottesville City Schools teachers. So we're glad that we're able to combine forces here. And Nigel, how about you go next?
Good morning, I'm Nigel and I work for the city schools and support their science, engineering, and STEM programs. Luther?
Science at UVA and do a lot of trainings like this.
I'll go next. I'm Jenny. I'm at UVA also, and I'm in STEM and now computer science education. I'll pass it to Eric maybe first because he's also on the team, and then maybe go to Shanae after that.
Hi, I'm Eric. I am a new PhD student with Jenny in the STEM education program, and I'll pass it to Shanae.
Hi, I'm Shanae. I teach algebra and 8th grade math at Buford Middle School. And I can pass it to Mr. Nunley.
Good morning, everybody. My name is Ryan Nunley, and I teach 6th grade math at Walker Upper Elementary School.
Rachel?
Sorry, I should have passed.
So I'm Rachel. I am going to be teaching 3rd grade at Clark Elementary School.
I'm Sarah Fitzhenry. I was a teacher librarian for a long time, but I'm the brand new learning and community manager for BirdBrain Technologies, helping teachers to bring creative robotics into their classrooms and curriculum.
Hi, Chase Rohan. I am the STEM specialist for the Boys and Girls Clubs of Central Virginia. So spanning Charlottesville, Scottsville, Madison, and Orange County.
Morning, I'm Tiffany Cobbs. I'm an instructional technology coach for Newport News Public Schools. So I'm in the Tidewater area.
That's so awesome. And Christy?
I'm Chrissy Hartwell. I teach kindergarten at Johnson.
Awesome. I think we caught everybody, right? Cool. So let me start sharing the screen. Okay, we are into week 2, and this week we are going to take you into some CS teaching strategies that you can incorporate into what you're doing with your computer science lessons. So week 1, we kind of took a little deep dive into computer science and what are the different aspects of it. And so now, what are some strategies that you might want to incorporate? And I'm full screen, so I'm not going to be able to see chat. So if somebody else can bring those up, and please feel free to interrupt me at any time, but all I see is the slides. All right, so we're going to go over several of them. Luther's really going to lead a lot of this discussion, but we'll be chiming in. There's some that are specific to CS and some that are just probably things you already do, but are very helpful in computer science.
Yeah, and just to comment on that, you already know how to teach. Hooray, keep doing it. These are some specific strategies that we found tend to work well when computing is involved. They may also work when computing is involved. Other things you do will work well. The hope is this will give you some cool ideas, not give you a checklist that you need to stress out that you haven't checked every box of.
Oh, thank you, Luther, we're not suggesting that you infuse all these into a lesson. Pick 1 or 2 to try out.
All right, the first strategy you want to talk about is the use, modify, create strategy. This is probably the most common way of introducing computing to people and in the world. The basic idea here is you first give somebody a computing artifact to use, and you just have them use it, explore it, see the code and see it running. And then you give them some specific things to modify, starting very small things. Change this 7 to a 5 and see what happens. These kinds of small things, moving up to larger and larger ideas. The idea here is that a program is essentially a set of instructions for the computer. And as the students get used to changing those instructions and seeing what changes, they'll get a better feeling of the correlation between the instructions and the behavior. which will help build confidence and understanding, leading eventually, as you make broader and broader modification goals, you can tell them to create something new using the things they have learned. So this is one of the most common ways of teaching people computing, particularly when they're starting out, but is also how we teach people new programming languages they've been programming for 20 years. We show them some code and they play with it. And then after they have a few questions, we teach them the rules. This remains dominant throughout all levels of computing instruction.
Yeah, and I would say, even if you're working in technology, almost always when you're looking how to do something, you're going to go find somebody, go find how somebody else did it, and then kind of make it your own. So it's a very, you know, in other areas, remixing or taking other people's work is not sometimes frowned upon, and it's really not in computer science.
Oh, there was a comment in the chat Jenny made actually about use modify create. Let me touch that really briefly. Scratch is great for this. That is true. So the Scratch programming language and its derivatives have been designed around the idea of use modify create, where it's really easy to remix other people's code. And we will hopefully be able to sharing you a little example where you can play with that as well later and this week.
I'm muted. Luther's created a use modify create example using Scratch. So that'll be one of the sort of, if you want to take a deeper dive and try this strategy out yourself, you'll have a link to that this week.
Eric makes a good point. If you're using somebody else's stuff, you should mention who they are. It makes people feel happy. All right. Pair programming. The basic idea of pair programming is that it's better to have two minds focusing on a task than just one. There's a lot of reasons why this is better. The usual model of pair programming is that one person is actually using the computer and somebody else is looking at the screen and offering commentary. And this has been shown to work in lots of ways. Some professional software development tools systems do this, and they're internal to the company. But it's also really useful in helping students learn, because the process of talking with one another about what they're doing and why they're doing it helps them think about what they are doing. So the important in this is that there is a switching and monitoring of roles. You don't want one student to dominate and the other one to play second seat. You don't want students stealing the keyboard from each other. They need to both have opportunities driving and navigating, as the roles are commonly done. And so it requires a fair amount of intervention to make it work well, because this is not naturally how most students do this. There's a variety of questions about sort of how do you pick the right pairs. There is ongoing research in this that will come up with contradictory conclusions. The common thing is you want the people to work well together. One of the most common things that make that happen is if the people both respect the other's knowledge. So it doesn't actually matter how good they are at what they're doing, but it doesn't matter how good they think the other one is. They'll be more comfortable if they think the other person is their peer as opposed to their superior or inferior. And you'll need to monitor this. You'll need to know your students. You'll need to know who gets along well and who doesn't. Pair programming is not the time I would suggest teaching people social skills. You're giving them a new task to do that can be exciting and challenging, and that can occupy their mind enough that you want the social skills not to be the dominant part of their thinking. Buddy programming is the weaker version of pair programming. If you don't have the bandwidth to carefully monitor their pairing and cause them to switch and force them to talk and share the computer and so on, then you just put them side by side, have them look at each other's screen and work together, but each do their own thing. This removes the sharing part. They each have their own device. They can each do their own thing, but allows them to still share ideas and so on. So it requires a lot less management. The research suggests there's a lot less research in body programming, I should comment, and the research suggests it has a somewhat lower beneficial pedagogical impact than the more controlled pair programming, but it works pretty well. We use it extensively, many other schools do as well, as a way of helping students share thoughts with each other, get through some of that experimentation mindset that's part of a lot of programming as they go along.
Yeah, I would say that this works really well for younger kids, kindergarten, first grade, second grade, where it's harder to kind of do pair programming and really have rigid, guidelines for that. This is a great way to kind of introduce them to that idea.
This is the challenging part, the frightening part, if you will, about teaching programming. Some student will write some code and it won't do what they wanted it to do, and they won't know why, and they will ask you and you won't know why either. Oh So this is the process of debugging. We have actually a separate video you'll get to watch about some common debugging strategies we found work well. But the basic goal here is to describe what you want the program to be doing. Make sure you have an internal consistent mental model, or the student does. To have the student tell you what they wanted it to do. Find what it's doing that isn't that thing. So and generally you want the first thing, because in a sequence of instructions, which is fundamentally what code is, if an early instruction does the wrong thing, everything after that is likely to be polluted by that bad step. So it's a process of figuring out where is the first place it diverged from what you wanted it to do. Then there's a level of experimentation, trying out things, putting in something to display, trying changing things, see if you can figure out, is that really what's going wrong and what went wrong? And then trying to fix that and change what it's doing. There's a lot of strategies we can talk about here. One we're trying to talk about in this general setting, you can actually make this a very useful thing to do with the whole class. If somebody has a particularly interesting bug, it's a great opportunity to display that to the whole class, have the class walk through the process of acting out the different roles in the code, talking through what's happening, understanding from this. Because a large portion of what you'll do in programming, because it's so easy to tell the computer what to do, is you'll tell the computer what to do and you'll get it wrong. And then you'll need to figure out why you got it wrong and try to fix that.
Yeah, and I think,
Do you have,
oh, go ahead, sorry.
no, I was wondering if you could speak a little bit more about this, because I feel like this could be a very frustrating topic to teach. How do you keep it so that both the students and the teacher, because this is such a good skill, you know, experimental culture essential to CS. How do you spin it more so that it's not frustrating and it's fun?
Yeah, that's a good question. And this degree depends to some degree on how much coding you plan to do. If you're going to spend a few days in your year doing this, then I would suggest the best way to do is give very small steps with regular check-ins so big bugs can't happen. If you're going to spend a lot of time doing this, then one of the things that we do in our introduction programming classes, we actually start by debugging things that aren't programs. So we have an exercise where we have them write instructions for how to make a paper airplane, and then hand their instructions to the person sitting next to them, who has to follow the instructions to the letter, but not to the spirit. And then they have to try to figure out how, and they realize how hard it is to explain things, and it gives them this fun experience. Once they've had that fun experience, we can then go and sort of refer back to this. There's lots of other sorts of things there. But the other thing to understand is this is part of the task of programming. And so there will be a level of frustration. It's more about setting the expectation that what we expect to do is create a draft program that doesn't work and then fix it. That's the expected process. The expected process is not to create a perfect program. That's a weird thing to do in the long run.
Yeah, and I do a lot of celebrating the bugs, like getting kids comfortable with sharing areas that they got stuck in, and collaborating is something you really have to be intentional about. And also I start by this use, modify, create, giving them something that already exists and letting them experiment around with that, and with the idea that you can't break anything. Like, yes, you'll get bugs, whatever, but you can always go back to the original state if something goes completely off the rails. So it's a lot of just opportunities to experiment and try things, and also a sort of a mindset of this is going to happen, and also brainstorming strategies for, okay, when this happens, how are you going to deal with it? One strategy is you just make one little change at a time in your code so you can see what's happening. Sometimes it might be you got to take a break, like you've hit a wall with this particular bug and you need to go do something else, different things like that.
Sarah had a really nice comment in the chat. Sarah, do you mind talking about how you put it in sort of the expectations or the directions like Luther was talking about?
Sure. If I were introducing something and step 1 was power your device, step 2 was write your code, step 3 was see what happens, and then step 4 would be like when it doesn't go the way you want it to, see if you can fix it. And so just putting it out there as not an option or something that will happen to the people that don't get it, but saying this is completely normal when you make your mistake, not if. When every single one of you makes this mistake, here's what you do. It's no longer, oh no, what if I make a mistake? It's just like, oh, I'm supposed to do that, and that's going to happen to everyone. And then it just seems to hit students differently when the mistake comes, because they're like, well, that was part of the process. I had to, it's written on the board. It just kind of lowers the risk factor, I guess, makes it less scary.
And it's worth knowing this isn't something you grow out of. The standard rule of thumb in software development lifecycle is you spend 90% of effort in what's called the maintenance phase, where you're debugging. And that's sort of the expectation of the whole field. Is that, it's not just, it's the classroom expectation, it's an expectation of programming. All right, pseudocode. At its core, a program is a sequence of instructions. And so you don't have to write the programming language to get the concept of a sequence of instructions across. And pseudocode is the idea of writing sort of using English or whatever language you want, pictures, whatever you want, to get across the individual steps while still writing down the structure of what you want to have happen. This can be really useful in helping students understand what they're trying to do, figuring out what the big pieces of what they're trying to do is, getting past obstacles. So if they're having trouble with one part, it can be useful to say, well, we'll just pseudocode that. Just say what it's supposed to do. We'll come back to making it actually do that later. It can also be useful debugging exercise. To ask students to describe what their code is doing, you're asking them to verbalize pseudocode, right? Describe the steps you wanted it to do, what steps you think it is doing, but the computer disagrees with you about what's actually happening. So pseudocode is a very valuable technique. Depending on how old the kids you're teaching are, you may not want to show them anything that looks like text here, but you'll still want to have some concept of a sequence of steps doesn't have to be expressed in code. And many of the unplugged kinds of activities you could argue are only pseudocode. We don't deal with the formal code. We stop at the pseudocode that can still teach you dramatically valuable lessons in the programming space. Code reviews are a technique you can use in your classroom in lots of different ways. They can be used for debugging. They can be used to help catch up some students. They can be used to help people introduce new ideas. The basic idea here is that you're going to show code to the whole class or to a group of students together, and you're going to have them talk through it. You can talk about what does it do. Sometimes when I'm introducing new topics, I will show code that they haven't seen before and ask them to guess its behavior. As sort of an introductory kind of thing. You can do it to help people debug. You can do it to help them walk through the process and understand what's happening. You can also ask them how they can change what they're doing. Just as there are multiple ways of saying things to humans that have the same idea but expressed differently, there are multiple ways to say things to computers. And so you can often ask questions like, how could you make this shorter? You can tie it back to other practices and talk about how would you describe it in English, getting at some of that pseudocode. You can compare different implementations and have students try to guess circumstances where they'll behave differently and so on. And all of this can take that, what can sometimes feel like a somewhat chaotic out of debugging. If you aren't careful about it, you can end up sort of being trial and error. And then once you get something, this code review process can help turn that back into deeper understanding that can be applied in the future.
Should I take this one, Luther?
Sure.
So this is something I like to do a lot with, especially projects where there's going to be a little bit more creativity involved, creating a game or an animation or something like that. Having the class discuss and sort of create the rubric for how their program is going to be assessed, like what everybody agrees what are sort of the minimum things that need to be included, and then you might have some bonus things. It helps clarify the goals for students and make them feel ownership. It also gives them a level of freedom and creativity that they enjoy. But you also want to make sure that you've sort of created your rubric on the side and infuse those if they don't get brought up by the students. It also helps set up appropriate scope because some projects can go on and on and on. And so you want to make sure that with whatever time frame you have to do the project, that you're helping students set realistic goals for themselves.
I'll add one other benefit of this, and really just of having criteria at all. Because students can spend a lot of time debugging, they can feel frustrated even when they're making progress. And so having a list of things they're hoping to achieve can help you point out how much progress they're making and that they are succeeding if they're having a couple of frustrating debugging sessions back to back.
Yeah. So the example I have here is actually fourth graders were designing math coding games for second graders. And so this was a list of things that they thought, should be included in a coding game for second graders.
All right, Think, Pair, Share. You may already be familiar with it. This entered the computer science education space from other disciplines. The basic idea here is it's a three-step process. You give students an open-ended question to think about independently, and you don't let them talk to each other while they think. And after they've had time to think, you have them pair up and share their thoughts in pairs. And after they've had time to share their thoughts in pairs, you have them share with the class. This is a good pedagogical strategy in lots of circumstances. It is caught on very well in computing, in part because computing tends to have a lot of these questions are sort of in the mix of the open-ended and you can get it wrong space. When we're asking how would you do something, there's lots of answers, but some of them are wrong. And this process allows students to have the time to internalize, consider, check with a neighbor, make sure they're comfortable before they share. It tends to result in a lot more sharing, as well as engagement of all of the students, including those who will not generally volunteer.
So Luther, you probably noticed that I couldn't find a good image for Think, Pair, Share, but I kept thinking about the rubber duck.
Should we talk about rubber duckies?
Yeah, talk about the rubber duck.
Sure. There is also this notion of rubber ducky debugging. And the idea here is this actually used in industry in some cases. Often when you try to explain a bug to somebody else, there's a common process where you start to explain the problem, and before the other person understands what you're saying, you're like, oh, I get it now. And then you fix your own problem without the other person having to say anything. And this is so common that there's this idea of a rubber ducky debugging where you just talk to a rubber duck. You explain your problem to the rubber duck and it will solve your problem for you. And this can be thought of as you're pairing with an inanimate object. There have actually been studies about what you should talk to. It turns out that it needs to have a face. It doesn't work as well to talk to an eraser as it does to a duck or a teddy bear. But this is another thing you can do. And this can also be useful. There are teachers I know that have found this. They'll give out rubber ducks and they'll just have them always around. And whenever you're frustrated with anything, you can look at the rubber duck. Even if you're not allowed to talk, you can telepathically talk to your rubber duck. And this can have a surprising effect. The process of explaining the situation can help solve this. There's a question in the chat about what objects were tried during the study. It's been a long time since I looked at that paper. If you're really interested, I'll try to dig it up again.
I noticed when I was looking up, I saw several teachers who had bought rubber ducks in bulk and gave them to their kids. So this is something, exit slips are something I use a lot, and they're really useful to gather information, especially if you're doing a multi-day project over a lot of classes with a lot of students, and it's hard to keep track of where everybody is. Having them share that with you in an exit slip really helps you track that engagement and troubleshoot problems. I've also done this as these questions are what is part of something called the Agile stand-up meeting. So this is done in professional settings where a team gets together and they go, quickly through what did you accomplish, what are you going to work on next, and are you stuck? So it's also a very interesting thing to do with whole classes so everybody kind of gets an idea of what people are working on and they might be able to help each other. I've done this with as young as third graders.
Again, this is something you can use in any class. Anytime you're not sure how students are doing, this can be a useful thing. In my experience, it takes a little while for them to get used to it. So if you want to get the full benefit of exit slips, you'll need to do it several times so they get used to the idea that you're going to do it before you'll start getting useful information.
Do you ever give them multiple choice? How do you teach them? The middle schoolers, these questions could be kind of intimidating. Like I would get lots of I don't knows on it.
So one thing I have done, actually even in college, I once printed out frowny face to smiley face scale, where I had, sort of slightly frowny, very frowny, bored, slightly smiling, very smiley. And I just had students circle one as they walked out of the room. And that already told me quite a lot and got them used to the idea that I wasn't looking for details, I was just looking for information. And then from there, I then add a little blank underneath that said, what's a question we didn't answer? And you can do those kinds of structured things as well. I've sometimes done the, what did we go too slowly over? What did we go too quickly over? Those kinds of questions. Exactly what you're going to ask will probably depend on the level of students. And I haven't taught really young students. I know, Kim, you've used this at third grade. Any guidance for that?
I think I just use it all the time. So I think, just over time, the expectation is, oh, she's going to be asking these questions. And it really is nice to do it, first as a stand-up, sort of a full class experience, so that the class can see what is happening and why it might be useful. And it doesn't even have to be every student, if there's a couple of projects going on you want to highlight or whatever. But yeah, I just do it all the time.
There's a question in the chat about, is it better verbal or written?
I think depends on time and how much time you want to spend on it.
And size of class.
Yeah.
There's certainly value in verbal. It helps students realize that other people are also stuck with things. It helps them realize their successes when they hear other people talk about the successes. There's a social benefit to the verbal, but it takes extra time, and that time scales with the number of students. So the larger your class, the more impediment to verbal there is.
Oh, one more question. The word agile stand-up meetings, are you using that as impromptu? Is that a synonym for that word?
No. Agile development process is one family of software development processes. It's a term of art in software development circles. It basically refers to a process whereby you make a large number of small goals instead of a large overarching plan. But the reason we mention this is because if you do a search for Agile stand-up, you can find stuff about this and so forth. Or if you've already engaged in software development, some of our people have and will know what that means.
Yeah, and I just like to let the kids know that this is something that people are doing in the real world in their real jobs. So it's not something I made up.
Yeah, we actually—
It might change by the time they get to high school, right? It feels like it changes really quick.
The Agile development process has been around since, when was it? The late 90s. So for computer science, that's really durable, surprisingly old. We actually started doing these in UVA because our students would go off for summer internships and jobs and come back and say we should do them. So we actually got them from industry, not the other way around.
I was wondering maybe if we could stop and just take a break and just discuss, like, so we just presented a whole bunch of strategies. Just wondering, like, if any resonated with you, maybe like, or, like think, pair, share, and exit slips. They seem, pretty, you might be already using them in other contexts, right? And then just bringing them into computer science. Yeah, I was just curious if we had more questions or more input from everyone. We could also do a think, pair, share where we put people together in groups first, and then, yeah, to model what we should be modeling.
I just wanted to comment. I like the pairing aspects that you all were talking about in the slide, because I'm sure it's a trend in every classroom, but I've just seen it at my school. There's a high success rate for kids gaining material and then building on their knowledge with certain topics and content if they're paired up with an individual, or sometimes a small group, depending on what the size of the group is. But more specifically, based on what we were talking about, the pairing up with an individual, I think is I really want to try to figure out some way to incorporate that in one of my lessons with what I'm doing. I think there's, especially with the content, what we're talking about now.
An important thought on this. It requires more brain power to think with a partner than by yourself. And you will get tired doing it. As we like to say in our classes, this can take a toll on your brain. So expect some downtime, some breaks, some unstructured time. It may look like they're being less productive occasionally. The research in the paired programming for like professional development suggests you get about 170% the efficiency that you would if you worked individually.
That's that. I mean, I'm just gonna go ahead and just humbly say that shocks me. I just, especially with coding and with programming and watching kids go to work, I've seen, I guess a learning aspect for me. Then I guess I would think, without having seen it in play per se, that working with somebody would make something go deeper and maybe be easier as well. But maybe, I mean, clearly that's not the case.
What in general happens is the other person is thinking slightly differently than you and catches things you don't. And so more of the complexity of the problem is in your mind at a time. So you make fewer bugs, you move more rapidly towards the goal, but you have sort of a brain and a half of effort that you're putting in.
On the flip side, I think Luther's saying it's like really easy to get like one track minded as a single student. And that can be a detriment to creating creative programs.
I was thinking a lot about like the debugging, because we'll do that a lot in math where we'll, our kindergartners will work out some type of story problem, mostly by using drawings and visuals to solve it. But if something goes wrong in somebody's, we'll often put it like up on the Elmo and we'll say like, what do you notice that's not right? But not necessarily sequentially. So now I'm thinking like more about like having kids talk through exactly like the steps of what they did. And then we can locate and isolate like where it went wrong, as opposed to just like what went wrong.
And one of the nice things about code is that it runs sequentially, but it's all visible, right? You don't have to remember what step 3 was, it's there. So it's even easier to do that if you've put that process in code than if you just did it yourself.
And what that could look like in kindergarten could be like, step 1, right? Find the value, not find values, but it could be something like that, right? For at a kindergarten level. I'm just trying to think, my daughter just went through kindergarten. So what would she be? She'd be able to make the list, right? And then try to figure out like when in the story problem or kind of the procedure for the story problem. And that would be, I mean, I can ask Kim and Luther and Eric and Nigel what they think, but a slam dunk integrated lesson for mathematics and computing.
Something I will sometimes do when I'm working on the board to work out something is I'll just occasionally switch color markers so that I can, when something goes wrong, I can say, oh, it happened when I was using the blue marker. And it adds a temporal component to my own thinking. And something like that may also work for whatever you're having the students do. It helps reveal that there was a process to what they were doing, which is a key integration concept that we have in the CS standards.
I'll say on the flip side, math is a good one because it's like logic based, but like writing, like I think we build this into teaching writing. Like we do a draft sentence, we do a draft paragraph, we do a draft essay, and that's like not graded. It's okay. Just turn in your ideas and your basic thing. And the same thing I think is true in programming. Like just get it all out, try to get it working, and then go back and see what's happening. And that's okay. And we like break down the sentence structure because there's rules to a sentence. And the same thing is true with programming. Like there's rules we have to follow and we get a specific output. So we already do debugging in our normal things to build these skills and strategies for students.
It goes so beautifully with writing poetry, because if you change one word in the line of a poem, it can change everything. And so I think about writing a poem and swap out one word and see what happens versus write a line of code, swap out one word and see what happens. And those two things could be really neat to try together.
I think similar idea I see with pseudocode, it being like an equity tool. I'm hoping to work with more ESL students, to having them be able to write in their own languages or students who can't write, being able to like draw in their own languages or draw in their own ways. This like process to decompose like their tasks. But I mean, so this is not a fully formed thought, but I think I could see that as an equity piece of being able to see what they're thinking.
Yeah, there's also an interesting, I've seen it not only once, but I once saw a group of computer science educators who were asked to write a program where they just translated all of the keywords in the programming language into Spanish. And all of these people that didn't know Spanish but knew the language were surprised by how difficult it was when there wasn't the word for, it was some other word instead. And I think depending on how much you want to invest here, there is also that opportunity to use this as or an equity education, helping people understand the challenges their peers are going through.
I love these ideas. I know I put it in the chat, but these are such great ideas. I was just thinking of like, yeah, there should be so I love the thinking of how people can express their understanding in different ways in different languages. Like love it. Also how there's like being a reader and being a writer, there should be being a computer scientist or something like that to go alongside that. But yeah, no, great ideas.
Awesome. Thank you all so much. I'm going to go back. So Jenny, I'll just say a little bit about this and then I'll let you dive in. But the reason I picked this image, so
it sounds great.
Our goal is for you to be integrating CS into a subject area, to something you're already doing, and it not being necessarily an independent thing, although sometimes you might have to introduce concepts independently. But there is just so much opportunity for integration, as you all were already talking about. I was at the CSTA conference, Computer Science Teacher Association conference, last week, and they were sharing these amazing tools for math integration and world language integration and English integration. So I'm trying to share a lot of those out through resources that we have. But what I love about this image is, it's bringing in science and literacy and math, and where the intersection is patterns, problem solving, representation, and sequencing. But it's also bringing up play and social emotional. Now this is from the K-12 CS framework for K2 for early learners. But I would like to say this should be for all learners. One of the things that computer science gives you the opportunity to do, because the tools are so amazing, like Scratch, there really is an element of play. And there really is, and in fact, some classrooms that I went into, the teachers were uncomfortable with this level of play because they didn't necessarily think the kids were learning. But I just want to encourage you to take advantage of the playfulness of the tools that are available to do CS integration.
Yay. So hopefully, I don't know, my internet has been spotty, so I apologize if this is not coming through, just like tell me. But I'll just make a brief statement and thinking about it as a spectrum as well, so that, on one side, it's all CS, on the other side, it's all within the content. And we're really trying to find somewhere in the middle. And so it doesn't matter, to what extent in the middle, but just thinking about being able to integrate a little bit of computer science into something that you're already doing is like we were talking about with Christy, and the math, sort of debugging in math is great, all the way out to maybe doing something that's a little bit more like purely CS. But we're really excited to work with you to be able to integrate computer science into your classroom in a way that makes sense and has the most meaning for each of you.
Awesome. So toward that end, we have identified several lesson repositories. One is actually from myself. So I taught, I worked with teachers to help them integrate computer science in K-8 for 6 years. And through that work, I created a lot of different plans. And so one of the things you're going to see linked is resources, is all these different plans, and they're in various states of ready for prime time. but it does identify, if they're like an activity is sort of a one thing, a unit or a project is longer term, where you might do integration, sort of the grade levels that I did it with, the tech requirements. And then over here is sort of the status. So if it's Go Open VA, that's a tested resource. We shared it already. That's really good to go. If it says Misbit to update, that's one that I still need to go back and do some refinement on. So if you find a lesson that has that and you're excited about it, let me know and I'll prioritize that to make it more accessible. But if you don't find anything in this list, I've also linked to a bunch of other CS lesson repositories. So there should be no lack of resources out there to get started. And what we're asking you to do for this week is to find a lesson that you can remix and add 1 or 2 CS teaching strategies to it.
Now, if you're like me, you probably look at that giant list and you say, oh no, there's too many, how will I pick? This would be a great use for our office hours. You're welcome to come talk to us, describe your general situation, and we might be able to point you in a good direction.
Awesome, thank you for that ad for office hours. We want to see you. Then on top of that, Eric has created a lesson plan template. So I'm gonna let him talk through sort of the expectations for that.
Sure. We in hopes to make the lesson plan situation a little bit easier on you and to make it easily comparable to everyone in this group and anyone who's using it. We tried to make a lesson plan template. Just in basic use, I created a short video that we might actually update, but it's a work in progress. So if something doesn't work, just let us know and we'll adjust and change. We're trying to make it a little easier, but just start by selecting the grade that you're teaching or you'd like to teach your lesson. And it automatically populates the SOLs for each of those sections. So you can put in your title and then put in your Virginia SOLs. If you're like, I don't have those memorized, that's okay right now. Eventually, I'm sure you'll memorize them all. But at the bottom, there's a bunch of tabs. So if you're a Google Sheets person, you can just click the CS concepts, the SOLs, and they're all listed. So you can search for them or just look at them and go through your grade level. So that should help. And you don't have to go through multiple resources. Once you've selected a grade and an SOL, if you're integrating your lesson into, let's say, science, you can drop down, pick your category, the SOLs, and it'll pop in the strand for you. So that should hopefully keep everything a little more organized on the SOL side. The CS framework that the Virginia Department of Education posted has concepts per grade. And that's in the appendices of the framework, but those are all listed here. And again, those are in one of the tabs as well. So if you just kind of want to dump some concepts, so you can kind of see like, oh, I've done a lot of stuff on loops. I should probably start spreading out and doing other activities. And then now that we've shared the CS teaching strategies, those are all listed in a dropdown as well. And then you can add a little bit of reflection in that place as well. So that should give you sort of an overview of the lesson plan itself. And again, we can do the same for equitable strategies, which we'll go over next week, I believe. So we'll go into further detail. The rest of the lesson plan template is mostly adding in text and things like that. If there's something you need or you are like, well, it's lacking, just let us know or feel free to add it and send it over to us. This is just kind of an open document that we're hoping makes it easy for you guys and for everybody to share everything. If you want to tie in a Google Doc as well, I think Kim had an example where she had a separate kind of outline of an activity or a lesson, and then she just linked that within the document. You're welcome to do that as well. But we're hoping this all the stuff we just showed you is kind of the basic overview so that you have one spot to put everything in.
Yeah, so we'll be sharing samples of how you can use this, but you're going to link to other resources that already, art lessons or activities that already exist. So you can link to those in the lesson at a glance, or you also have the opportunity to go ahead and, fill out for a lesson. And I guess you can just copy this if you want to keep adding more parts to the lesson.
That's right. And in Kim, at the bottom in the helps thing, there's just like a short PDF. There's 2 links there to the video, which I think we'll update, but there's also a little PDF document there that just has like a quick cheat sheet. If you need to, like, what was the order again? So hopefully that'll kind of help you. And we'll just try to keep updating that stuff. But if you have questions, again, just reach out and please ask.
Yes, our hope is that when you're sharing the lesson with us, if you're CCS, you're sharing it through the Canvas, or if you're CS Institute, we're going to, I got to create a Google Drive for you to share it. This is what we're hoping you at least fill out this top part and then link to resources that you're using. That's kind of what we're looking for.
And Kim, as a Google thing, I don't think we're going to share an editable version, but you can make a copy and save it to your drive, and that way we keep the template.
Yeah,
So just,
no, that's what I did already, I think.
okay. Yeah, I
I
just
went
wanted to
to,
make,
let's see, make sure. Yeah, it's going to make you make a copy.
perfect. Thanks, Kim.
And we'll just remind you, we do would love to meet with you. We have a variety of availability to do that. If you'll reach out to us, that would be great.
Thank you all for your time.
Yes.
A bunch of other, of course, as always, we have other videos and materials for you to consume on your own. We will have other activities coming up, but thank you all.